All right, guys. So in the last stream, we were discussing what happens when you put a spaceship at the radius of a white dwarf or a neutron star. And really, the question is, what sort of tidal forces would we have to be concerned with on our spaceship when it's at this radius of either the white dwarf or the neutron star? And we did two calculations just to look at what the tidal forces would be. And with one of them, I made a slight error. So with the radius of the white dwarf, so basically I went on Wikipedia and saw what some typical values were. And on Wikipedia, it said that you could probably pull a white dwarf radius. It could be somewhere less than 2% of the solar radius. And so I chose 1% of the solar radius, which is about 7 times 10 to the 8 meters. However, in the calculation, I actually used 10% of the solar radius. So have to make a quick modification to our final answer for that one. So I'm going to do that quickly right now. And so instead of it being an R value, so I'm going to highlight it down here, make this font a little bit bigger actually, so you can see it better. So instead of it being an R value equal to 7 times 10 to the 7 meters, it should have been R equals to 7 times 10 to the 6 meters. Which is actually very important because when considering the equation for the tidal force, it's proportional to 1 over R cubed. And so when you're off by a factor of 10 in the radius in this situation of the white dwarf, you're actually off by a factor of 1 over 10 cubed, which is, or in this case, it's actually, I'm sorry, 1 over 10 to the negative 1, that quantity cubed. So I was off by a factor of 1,000 as far as the tidal force is concerned, which is very, very, very big. So I'm making the correction now. And it's really easy to implement this correction. No need for a calculator to do it. So this is 10 to the 6. We know this is going to be a factor of 1,000 more. So instead of this being in units of kilonewtons, it should be in units of meganewtons. So I'll just put I think it's capital M actually, for meganewtons. So that's 10 to the 6th power. And given these corrections, it turns out that the differential acceleration that you can also calculate from this, just by dividing your tidal force by the mass of the spaceship, will also be increased by a factor of 1,000 as well. So this is actually going to be a differential acceleration of 200 meters per second squared, which is, what is that, a factor of 100 times more, or sorry, that's wrong, 20 times more than the acceleration that we experience here on Earth's surface. So with that correction, we can go ahead and we can move on with the rest of our problem. Yeah, powers of 10 can catch you. So let me go ahead and pop out the chat so I can see everyone's comments. All right, and so the next step, of course, is to now link all of this information into trying to see exactly what would happen to our spaceship when it's at this radius of either the neutron or the white dwarf star. And so to do this, I'm going to introduce a little bit of some animations that I've kind of grabbed online, and not even so much animations, just pictures of what I've grabbed online to kind of help us better understand the problem. Now, I've never done this problem before, guys, so I'm actually just thinking through it along with you guys. So if you guys see something that you think is not quite right, let me know. I'm going to definitely check it out. So first things first, we need to be able to input some of these pictures I have. And we'll start off with how we're basically viewing the tidal force. So let's do this. Gotta quickly pull up some stuff really quick. Give me one quick second. Let's see. All right, back here. And so I believe the name of the image I want to pull up is going to be tidal force. That's it. Oh, I want that to be centered. That's. But basically, the way in which we should be viewing this, and I've drawn a very simplistic view of what I'm thinking of the shuttle as, and of course I'm disregarding the very head of the shuttle to make the calculation easy. But the idea here is that we just basically have a cylindrical tube. So I think I can put center actually. Is it like begin center or something like that? Actually, I'll worry about centering and stuff a little bit later. But the idea here is that we have our space shuttle, and it's aligned radially or along one of the radii of our star, whether the star be a neutron star or a white dwarf. And so what we end up getting is the fact that the end of our space shuttle that's closest to the center of our star is going to experience a force greater than that of the force you're going to end up getting at the other end of our space shuttle. And this is exactly what our differential force is. It's going to be the difference between these two forces. And so, with this picture in mind, we need to be able to take this view of and this is the exact reason why our space shuttle will end up experiencing a lengthening that's going to be along the direction of our force. We need to be able to take this view of the shuttle and kind of change it such that we have this view. So I'm going to add another graphic. And I will center these in a second because I don't like the way it's formatted. So I'm going to center it. All right, so this one. Take this view of our shuttle and kind of change it so that it looks like this. All right, let's kind of minimize. Let's kind of shrink this so that you can see the entire picture. And so with looking at this image, our objective is to kind of, and primarily I want to focus on the blue image, or the blue cylinder. The idea here is that, or no, I'm sorry, the red cylinder. The idea here is that instead of the forces being in the same direction, we want to be able to have two forces acting at both ends of the ship that are in opposite direction but equal in magnitude. And note, for this particular drawing, this is actually the drawing for what you understand if you're trying to understand tensile stress on a cylindrical object. Excuse me. And so the idea here is that if you start off with the blue cylinder and you apply two forces to its end in opposite direction but equal in magnitude, you can basically stretch the cylinder. And so we're basically trying to do the exact same thing, or we're doing the exact same thing with the tidal force, except that the force vectors and their magnitudes are kind of different. So we need to kind of reimagine this picture into this picture, just so that we can be able to work with the math that accompanies the idea of tensile stress. All right, but really, I also made another image to kind of better get a better picture of what we're actually dealing with, because this image actually corresponds to having a solid cylindrical object, whereas our cylindrical object is actually hollow on the inside. So we're really kind of actually dealing with an image that looks more like this, or a situation that looks more like this. And so this actually kind of changes how we should approach the problem, because in the previous picture, like I said before, it was a solid cylinder. But now that we have a hollow cylinder, we can't take the entire surface, the cross-sectional area of a solid cylinder. We have to actually use the cross-sectional area of a cylinder that's hollow. Okay, with that said, we can now move on with the rest of the problem, actually get back into the math of it all. "20G, not spaghettification, may kill people, definitely throw them to the floor, and certainly kill a heart patient like me." So yeah, you're right. 20G would definitely kill a human being, definitely. So let's go ahead and let's see exactly how bad the damage will be. And so much of this is going to rely on, of course, and again, this is a very simplistic calculation. So I probably should even state, some of the assumptions I'm making here. That's actually a good idea. Again, I haven't worked this problem before, so stating what the assumptions are is important. That way, we can all understand exactly how we're working this problem. If your assumptions are different from mine, then that can throw things off for our understanding. So first things first, we're assuming, of course, that we're not concerned with any sort of extreme temperatures. So let's just assume that the star has had enough time to cool down, such that the temperatures is similar to temperatures we experience here on Earth. And it's important that we kind of assume this one particular assumption, because if the temperature is too cold or if it's too hot, given that the temperature could be either too cold or too hot, the material of our space shuttle will act differently. And I'm pretty sure that the values I'm going to get right now for this problem are going to be for temperatures that are kind of within the normal range. That is, temperatures that are very similar to the surface temperatures we get here on Earth. So assuming the temperature is similar to the temperatures we experience here on Earth, of course, that means that the star, of course, would have needed enough time to be able to cool down to those temperatures. Another assumption, specifically with neutron stars, we're assuming that the magnetic fields let's just assume magnetic fields are negligible. I'm having a problem spelling negligible. And I still misspelled it. There we go. Let's just do that. There we go. All right. So another thing that we need to probably assume. What do you guys think? Oh, wait. So I think rocket sled pilots survived it. So there have been people who have experienced 20G and lived to talk about it? It's pretty impressive, actually, if that's the case. But let's see. I'm also going to assume one more thing, that the internal pressure. I'm going to assume that the internal pressure is also negligible and will play no role in our problem. And I think this should be good enough for being able to continue with the problem. Yeah, I think this is good enough. And so we also need to know for this problem what would be the tensile strength of our rocket, of our spacecraft. So for this, we're going to go to online resources, because I don't know exactly what sort of materials are being used nowadays for spacecraft. So let's go ahead and see what online resources state. So let's do this. So just give me a second to quickly open up a web browser, and I think I should already have things set up so that it'll show perfect. All right, so spacecraft material. Let's put it that way. Actually, we're actually using a particular spacecraft. I think it's actually the BFR, but yesterday we said the BF, or the last stream we said BFS. Let's see. So the BFR rocket. Let's see if it just happens to have. So the details include the very large size construction material. It doesn't state exactly what the construction material is. We might just have to end up picking a material for it. Carbon fiber. Okay, we're going with carbon fiber. Survived 35G. I couldn't imagine it. Oh man. I'm pretty sure every single organ in his body shifted in the opposite direction, which I can imagine could be quite painful. I wonder how long he was able to survive that. All right, so we're going to use carbon fiber as our as the material for our spacecraft. Is carbon fiber a material that's commonly used for spacecraft? Just by itself? I remember when I was an undergrad, we used carbon fiber for the rockets the rockets that we were using for a competition, but I don't know if carbon fiber is strong enough, for like space adventures. Let's see. So we want to use carbon fiber. Let's see if we can find the tensile strength of carbon fiber. So tensile strength of carbon fiber. So it's saying here that the ultimate tensile strength of carbon fiber is 3.5 gigapascals. All right, let's go with it. So if I'm understanding tensile strength correctly, this corresponds to the maximum stress that a particular material can withstand. And if you go past this particular stress, the material will be pulled apart in this case. All right, so 3.5. Let me go ahead and write that down. Okay, so it hasn't been used yet.
Okay, so
It's a property of the resins that matter. Okay. Okay. So is it fair? Do you guys think it's fair to use? What you saw an estimate of 1,200 megapa, which is on the same order of magnitude as what I've just seen, right? But we can use this value though. So 1.2. So I'll use this actually. I think it's only like a factor of 2 less than what I just saw online. Oh wait, are you guys able to see what I'm looking at? You can see what I'm looking at. So online it says 3.5 or 3,500 megapascals, which is like a factor of 2 more than what you're, a little bit more than the factor of 2 than what you're stating, Larry. So we're gonna use your value. So 1,200 megapascals. All right. So with that, no indent. So this is going to be the pressure, but it's tensile. So tensile strength of carbon fiber. Construction material. All right, and so what that was, it was 1,200 MPa. All right, and if I'm not mistaken, the Pascal is an SI unit, so we should be good to work with this. All right. So now what we need to be able to do, of course, is turn our differential tidal force into a force that we can use for estimating what the pressure would be on our spacecraft. So So to do that, we need to reimagine the forces such that it matches the force description for tensile stress. So to do that, I'm going to make the assumption that the differential force, and I think this is a fair assumption, the differential force that we get from tidal forces must be equal to the differential force that we'd get if we applied an equal and opposite force at both ends of our spacecraft. So let's go ahead and do some math for that. And so in general, I think I'm basically stating this, that differential force that we're getting from pulling on the spacecraft with equal and opposite force at both ends, I think that gives us the 2F must be equal to the differential force that we get from our tidal force. So let me go ahead and switch scenes so you guys can see what I'm doing here. Let's scroll down. And so I'm assuming this. That given this scenario that we're seeing here, where we have equal and opposite forces tugging at our in this case our space shuttle at both ends, that the sum of the difference between these two forces, which is basically going to produce 2F, has to be equal to our differential tidal force. And really, I guess the way in which I should actually put this, so that makes sense, is that, of course, defining a coordinate system where up corresponds to positive values, down corresponds to negative values, we basically get that the force in the upward direction minus the negative force in the opposite direction has to be equal to the differential force that we're going to get from our tidal force. So this gives us 2F is equal to delta, or the tidal force, which basically gives us an F fraction over 2. Let's reformat that. So this is the force that we'd have to have if we were going to be trying to pull at both ends with equal and opposite force. This would have to be what the force would have to be equal to. We can plug in our value. Let's do this first one for the white dwarf actually. So white dwarf. I'll just put white dwarf right now. I know I'm not being very descriptive with that, but I'll probably change it a little bit later. This is going to have to be equal to, and I think we end up calculating, what was that? For the white dwarf, we calculated a differential force of 1.9 times 10 to the third power, 6 power newtons. And again, because we're working strictly in terms of SI, I'm not going to worry so much about incorporating the units. Taking a quick moment, guys, to look at your comments here. Hey, Linzo Brawls. Welcome to today's stream. Hey, Susie. In fact, I'm so rude. I didn't say hi to everyone. Hi, Phoenix. If I see your names, guys, I will say hi to you. I apologize. All right. So what this should end up giving us, when dividing by a factor of 2, I am so inclined right now to just simply do some rounding. We're just going to basically say it's on the order of 10 to the 6 newtons. Because 1.9 is almost equal to 2, so that's good enough. So this is the amount of force we're getting in the case of using a white dwarf as the star. And so now we're imagining we have our space shuttle. We're pulling it from both ends with the force of a meganewton essentially on both ends. And so now we need to be able to determine exactly, well, what is the cross-sectional area that we're actually applying this force to? Again, going back up to our problem here, or better yet, let's go into this one, excuse me. A sub 0 represents the area that the force is being applied to. And in this situation, we're assuming that that area is it's not going to be the cross-sectional area of a solid cylinder, but of a hollow one. So basically we need to know what the outer and inner diameters are of our cylindrical space shuttle. And I think we end up getting that information the very last time. We're probably gonna have to assume some thickness because I don't believe we saw that. So I'm gonna scroll up top. Let's see. Wait, did we not write this down? Tidal force equation, mass, radius of white dwarf, mass and length. Okay, I guess we have to go back and get that information. All right, so let's go back and see if we can find it. And again, guys, this is kind of like a really I guess if we were sitting together in a room and we're just thinking up how to go about doing this problem, we should be thinking of this like that. That's the approach we're taking here. Very simple calculation. Of course, I'm pretty sure it's probably far more complex than what we're doing, but this is a nice way of thinking about it. So what I'm going to do is I'm going to switch scenes so you can see what I'm looking up here. And so I think we can go back here actually. Let's just go back to Wikipedia. And I think it actually might give us the information we're looking for here. So I believe in the last stream we did say we were looking at the second stage of the spaceship. And it has an outer diameter, I'm assuming this is the outer diameter, of 9 meters. However, for this to work, we're going to have to assume some sort of thickness for our cylinder. Make sure I'm not missing any comments here. Oh, I'm sorry. Let's see. Not golf. Haha. Golfer will argue with you for this. I guess we could do the calculation of 1.9 divided by 2, but I think it's going to be really, really close to 1. Okay, guys, fair enough. We're going to go ahead and calculate it out completely. All right, so if I took 1.9 and divided it by 2, all right, we get 0.95, which is 9.5 times 10 to the 5 then. Yeah, that's right, because 9.5, 10 to the negative 1. Yeah, 9.5 times 10 to the 5 newtons of force that we're pulling it at both ends. And so we were just now at trying to determine what the cross-sectional area is of our spacecraft, which we're assuming to just simply be a cylindrical shell, essentially, or tube. So for this, so cross-sectional area, we'll have to make some assumptions, of course, about its thickness. And so we're going to say A is going to be equal to the difference between the areas that you get from the outer diameter and the inner diameter. We know that the outer diameter is going to be basically 9 meters, which gives us a radius, gives us an area of pi r squared. So it's what is that, pi? And we basically get r outer. This is going to be squared minus r inner squared. So really we have to just choose what the inner radius needs to be. And I think here we have to also be careful because we don't want it to be too thick. So let's assume that it has, and we don't want the thickness to be too close to the actual radius of the spacecraft. So let's assume that it has a thickness of, I don't know, probably, I think 1 meter would be way too big. Let's go with like an inch thick. Are you guys cool with that? You think that's too thin? I get your point, Linzo. I definitely get your point. I wouldn't want my $100. Yeah, I think an inch thickness, is that too small? Probably a little bit more. But yeah, we need to be able to have a thickness for this. And I don't think they're showing any sort of thickness online. Yeah, 1 to 1.5 is adequate as far as units of inches. So yeah, we'll have to convert this, of course, to meters. And as Larry puts there, 2.54 centimeters is equal to 1 inch. So using this 1 inch and converting that to meters, we end up getting 0.0254. I think that's it. Or basically 2.54 times 10 to the negative 2 meters. All right, so and again, guys, very simple calculation we're doing here. Pretty sure there's some parts that aren't completely All right, Uncle Bill Drone, let's see what you got. Let's see, I don't know about thickness, but using thin aluminum shells to estimate a carbon fiber substitute is probably misleading. All right. So what do you think? For right now, let's go with 1 inch, and of course we can always change it. We'll go back to the previous scene, and given that we're only going with an inch, let's see, what would that give us? And so we're working at SI units. So the outer one was going to be, I think it was 9 meters. So it's 9 squared. And the inner one is basically 9 meters minus an inch. Which is still going to be a very small number. So let's see. Sorry guys, I'm just quickly doing this calculation on my computer. Let's see, what was that? 2.54 centimeters, so 0.0254, which gives us an R value of weight. That's 9 meters in diameter. So I actually have to use half of that, so it's 4.5. And so for this one, it's that divided by 2, which is 4.4873. Max volume divided by mass ratio. Show the BRS construction with carbon fiber composite fuel tank. All right, let me look at this link really fast, Larry. I'm not gonna lie, guys. This is actually a really cool problem. Let's continue to article. All right, gonna continue to article. So I'm reading through the link that Larry posted. So yeah, it's definitely saying that the tanks, and I believe someone even said earlier about the fact that it's the resin that's most important. And they make a statement here. Yeah, if you guys get a chance, definitely check out the link that Larry posted there, talking about how carbon fiber composite gives strength to SpaceX plans to Mars. All right, so getting back to the problem though, so we have our equation here. We need to go ahead and calculate what the cross-sectional area will be of our space shuttle. So throwing all this information into, let's see if I can just copy and paste directly. Oh, it's going to throw it up. Let's see. Get rid of outer. Get rid of inner. Replace pi by 3.14. Multiplication sign 4.5 squared. That squared. All right, that didn't work. Okay, this. So I just attempted to copy and paste the information right there in the PDF into my MacBook, and it didn't like some things. Let's see. Maybe it's this minus sign. It doesn't recognize it probably. Oh, there we go. And this is the final equation or solution we get for the area. And of course, because we're working in SI units, it has to be in units of meters. Oops. But I am definitely going to shorten this. So just 3.6 times 10 to the negative 1. And this is going to be units of meters. Oh, sorry about that. All right, so this is the cross-sectional area that we're working with. Of course, we're assuming that the thickness of our spaceship is about 1 inch thick. Okay. All right, so next thing we have to do here is, of course, calculate a pressure that we're going to end up having on our space shuttle. And so to do this, we basically just take the force that we calculated earlier and we divide it by the area, the cross-sectional area of our spacecraft. All right, so and guys, I apologize for going over time here. I'm seeing that I went over time, so pressure is going to be equal to the force per unit area. So force per unit area. And what this ends up giving us is going to be the 9.5 times 10 to the 5 newtons divided by our cross-sectional area of 3.6 times 10 to the negative 1. And again, guys, I'm just dropping off the units for now because it's all in SI. This gives us a pressure value of, actually I can just do this, 9.5 divided by, is that 3.6? 3.6. So this gives us 2.6, is that 2.68? 2.6, I'm rounding again, times, and this is going to be 10 to the 6th power. 2.6 times 10 to the 6th power. And of course, this is going to be pascals. PA. Which is the same thing as saying 2.6 megapascals. All right, so with this, now we can go ahead and make our comparison to what did we find earlier online? That the tensile strength of carbon fiber is 1,200 megapascals. And so we'll end up finding that the white dwarf will exert a pressure of 2.6 megapascals, which is much, much less than what the ultimate what the tensile strength of the carbon fiber is. So we can assume that we'd probably be pretty safe on the surface of a white dwarf, given these calculations. Of course, assuming that all the assumptions and the way in which we approach this is correct. However, the case might be different for a neutron star, and even more so different for like a black hole. So standard air pressure is about 0.1 megapascals. So this is definitely this pressure is definitely but yeah, we didn't do this case for a neutron star though. And really, I think all that would change for the neutron star is primarily our calculation for what F would be. Black hole would never see us. Yeah, because the tidal force is basically dependent upon density. But also there's that whole mass radius relationship with black holes. I will definitely remember that, Lenzo. Well, guys, the time is now past 1 o'clock p.m. and I really love this problem. It was a fun problem to work. If you guys want, though, you can continue the problem for what the neutron star would be able to do to our spacecraft. I mean, really, it seems as though all you would need to do is recalculate what the equal and opposite forces would be from a neutron star, given the tidal forces that we've already calculated. We need conclusions. Okay. So the conclusions for at least for the white dwarf. So based on the tensile strength that we end up finding online for carbon fiber, well, for a spacecraft that's composed of a carbon fiber material, which corresponds to an ultimate tensile strength of 1,200 megapascals. If we were to put our carbon fiber constructed spacecraft at the radius of a white dwarf, we should not be so concerned about the spacecraft being ripped apart in any way by the tidal forces that we'd be undergoing on the surface or at the radius of a white dwarf. So, oh. Would Spaceball 1 get crushed? Oh man, guys, I'm loving your comments here. So, and you know what? I have no real physical sense actually for thinking of terms in thinking of forces in terms of or accelerations in terms of g's. I mean, I guess my best would be to kind of figure out how many g's one's experience. How many g's does one experience like when they're on a roller coaster, and then I can kind of like get an idea because I've been on roller coasters before. All right, guys. I'm gonna go ahead and end the stream now. AC, yeah, for my AC is astronomy cast is 3 2. It's in about an hour's time, guys. So I will be coming by for astronomy cast. All right, guys. Thanks for hanging out with me, talking some good science here. I loved it. I hope you guys had a good time too. That kind of scares me. I'm responding to Phoenix's suggestion. They're not gonna do any like weird stuff like do loop de loops and stuff like that, are they? Because I swear I'd probably throw up and probably do a little bit of crying too at the same time. But if you think it's a good idea, I might. Okay, if you think it's a good idea, I might go ahead and try it. All right, guys. I'll talk to you guys later. I'll be back again on next Wednesday, um, after Pamela's daily news update. So I'll see you guys then. All right, guys. Bye.